Thanks for the introduction, Robert. Okay, shall I begin now? Shall I start? Okay. Hello. So, hello everyone. Welcome to my talk. The talk I'm giving today is about the quantum time complexity of divide and conquer, and this is a joint work with my co-authors, Jonathan Alcock, Alexander Spelovs, Troy Lee, and Miklos Santo. Okay. So let's start it. So, what is divide and conquer? As we know, divide and conquer actually is a very fundamental paradigm to design algorithms. So roughly speaking, the high-level idea is to divide the problem into some smaller sub-problems. Then we conquer each of them and combine them to solve the original one. And this idea was first used by Gauss in 1805. And since then, numerous applications have emerged up to the present day. So but we noticed that there are very few works on a quantum divide and conquer. And probably the most relevant one is in QIP 2022 by Charles Cotry, Kovacs-Dick, Sendarum, and Wang. And in their work, they are mostly focused on the time query complexity. But in this work, we are more interested in the time complexity. So here is a main difference. So let me briefly introduce you our main results. So as I said, this work is the first systematic study of quantum divide and conquer that looks at time complexity. And as we know, the divide and conquer based algorithm actually is very broad. So that's why we give this structured four-step framework to help analyzing and design the divide and conquer based algorithm. And as we are talking about time complexity, of course, we should mention about memory here. So basically, we consider two memories. The first one is QRAM. Actually, it's say QRAM after the tutorial, and the QRAG is called QQRAM after the tutorial. And we use QR and QW to denote the time to perform the memory operation here. And for simplicity, we can assume in this talk, and QR and QW is always upper bounded by the square of the log n, where the small n is the input size and the capital N is the size of memory. Okay. Okay. Secondly, actually, we consider the general conditions where some classical divide and conquer algorithm actually admits some quantum speed up. So actually, our theorem can handle the maximization problems as well as search. So in some sense, we can also improve some search problems. And as a result, we give some quantum algorithm for the string problems, integer problems, and also computational geometry problem. Okay. So what is four-step framework? So here is a very simple example, which we call the single stock, single transaction problem. So AKA triple ST, or just a stock problem. So given an array of n stock prices, we want to find the maximum profit that we can make by buying at the time I and selling at time j. Okay. Of course, because we are talking about divide and conquer, first step is always create or divide here, which means we divide the original problems into two sub-problems. And second one is we call conquer, because as you say, we solve the smaller problems, and the second one. So first one is 9 here, and the second one is 7 here. And so besides the conquer, actually, if you want to solve the original problem, we have to do some side work. So here we call it the complete. And for these problems, we should find the minimum value of the first half and the maximum value of the second half, and then we combine them. So that's why we call the last step is combine. Actually, we consider all kinds of possibilities or all cases here, and it gives us a final output, 12. Okay, this is a very simple example, but you may say it's too trivial. So what I want to say is that actually the steps can be more complicated. It's not always so easy. For example, here is a merge sort and here is a quick sort. As we can see, for the create step, the merge sort actually is very trivial because we always divide the problems in a half and a half manner. But for quick sort, it's not so easy. Actually, newly created sub-problems highly depend on the chosen value. So it may be, for the sub-problem, it can become very complicated. And also complete and combine step here is not so easy. Sometimes we need more complicated functions. So I should say in this talk, also in our work, we only analyze a case with very simple create step, and also the complete and combined step is not so hard. But you may wondering why we are considered so easy case, but actually it's not so easy. The case we consider here actually involve covering most of the interesting problems in the real world. Okay. So let me introduce you the first approach, which we call the bottom-up divide and conquer. And so I should say in this case, we only consider a very trivial create step. Just imagine a merge sort. And here's a process of a merge sort. As we can see, given some areas here, and we first divide the problems in a half and half manner, and until there are only two elements left in the subproblems. Then we do the merge, then output the result. And as we can see, actually, we have already know. So at the beginning, we have already know how to divide the problems. So in some sense, the subproblems are known in advance. So we don't need to consider about these things again because we know how to do it. So that's why we consider maybe we can replace the recursive algorithm with an iterative one. So we can directly go run the algorithm from bottom to the up directly. So that's why we call it a bottom-up approach. But it's not always the case, but only for the trivial create step. Okay, so come back to our stock problems. So without these constraints I less than j, the problem becomes very trivial because we can only use a quantum maximization finding to find the maximum value and the minimum value. Now we combine them to output the absolute value of the difference. But after with this constraints I less than j, so mainly we have to consider two cases here. So the first case is that the optimal pair of buying time and selling time are both in the first half, or both in the second half. And also the last case we can buy at the first half and sell at the second half. This is what we call a closing case. Actually, it's very interesting. It's always what we are looking for because only in this case we can solve these problems by the quantum maximum finding, and it's very it's the really place that we can solve it because for other cases we only do the divide. So okay, so as we know, this case is very interesting. It's always we are looking for. So now consider a case. So given instance, so the optimal value output I star j star is always fixed. So now we just imagine I star and j star are both occur in the second half. So after we keep dividing the problems until there are only two elements left in the subproblems. So here is like a creation tree, and we can always claim there must be a subproblem is the closing case that we are always looking for. So actually we can, if this is right, so we can just reduce our stock problem to this closing case. And what we're gonna do is that we can using the quantum maximization finding algorithm to find all the output optimal value over all the 2 to the t intervals of size n over 2 to the t. And we can do another quantum maximization finding over the length of the prefix t here. Okay, so we have a two-level quantum maximization finding algorithm. And is this a truth? But maybe not. So now suppose we have some quantum algorithm to solve the closing case of size n over 2 to the t for each t. As you can see, this one is for t equals 1, t equals to 1, t equals to the log n minus 1. And here there are two main challenges here. So the first one is the AT may compute the optimal value with some errors. So we have to control the errors through the maximization. And the second one is when we taking the maximum value over all output of AT. Actually, AT is a circuit of varying length and structure, so we cannot use a quantum maximum finding algorithm directly here. So how should we deal with it? So here's so let me tell you how we control the errors here. So given capital N functions, a function mapping some n some string of size n to the 0, 1. And now suppose we have a standard Grover search oracle, and each query, we suppose each query takes tau time. So there's a fact here. So with high probability, we can find the index j such that f sub j of x is equal to 1 by square root of n queries, and by the square root of n times the sum of log n plus tau time. And which is good. But now we have an erroneous oracle. So which means the query is not always perfect. And naively, we can repeating this oracle many times and doing a majority voting. But it turns out square root times log n queries can solve this problem. But I want to tell you is that in 2003, by Hoyer, Mosca, De Wolf, they proved that square root n queries actually is enough for solve this problem. And in this work, because we are talking about time complexity here, so we're also doing the time analysis, and it turns out square root n times the sum of log n plus tau time is also enough to solve this problem. And I should mention analysis for the maximization or the minimization actually is very similar here. I only show you the search case here. So after we have this result, so it's very important to list the Grover search and the maximization. So perfectly, we can control our errors here. And by passing this, after bypassing these challenges, then we can give our algorithms. So the first one, besides the stock problems, we also consider about the longest increase in substring problem, longest substring of identical characters, and also the longest 2, 0, star 2 substring, which is a very famous problem, well studied by the Arison, Greer, and Schaeffer in 2019, and also by Charles et al. And by our bottom-up approach, actually we can prove the quantum time complexity of all of these problems is square root n times log n to the 5/2. And only for the first problem, actually we reprove the result in the time complexity. And the last problem we consider is a k increase in subsequence. And for these problems, actually, so compared to the result in the Charles et al.'s paper, and our new algorithm by bottom-up approach actually can achieve the polylogarithm speed up. Okay. Oh, okay. So we have already seen our first approach, bottom-up divide and conquer. It can solve some cases where the create step is very trivial. But as I say, we consider a case with a simple create step, which is not trivial. So let's see a second case where the create step is non-trivial, but it still can be constructive. I will explain this later. And also a complete step is very simple, and a combined step we'll assume is always a maximization. Okay. So what is the constructive maximization problems? So given a string, so generally speaking, given a string of size n, we want to output some value p of a here, p of a. And of course, according to our four-step framework, we should create some subproblems. And here we create h of n constitutive strings, each of size n over m of n. I should mention that is for the constitutive string, it's not not necessarily to be a substring or subsequence of a. Okay. And next, so as we assume, we have a very simple, relatively simple completion function gamma. It involves 3 arguments: parent string, constitutive string number, and also the solutions on the subproblems corresponding to the constitutive string. Okay. And also the last step is a combined step here is a maximization, as I assume. Okay, if we here comes our meta theorem. So if we have a problem satisfy the conditions like a constructive maximization problem, now which means we can directly give a quantum algorithm and with its time complexity here. So how does it look like? So first of all, we compute a number of constitutive strings, which is h of n. Then we compute constitutive strings and return it back to the memory. And the fourth step is compute all the sub-problems in the superposition. Then it takes some time to compute the completion function gamma. And beyond all of them, now we consider using we're using a quantum maximization funding with erroneous oracle here. So here comes our time complexity result, and here is our algorithm. Okay. You may think it's very abstract, so let me give you two examples here. Okay, maybe I should pause for a while. Great. Okay. Here are two applications. The first one is a Clay's coverage, which comes from the computational geometry. So given n-axis parallel hyperrectangles and a base box gamma in a d-dimensional spaces, the question is to decide if the union of the n-axis parallel hyperrectangles cover the gamma. So here's a picture. So as we can see in this picture, the right dot actually is not covered by any hyperrectangle. So that's why it's a negative instance here. Classically, by Chen in 2013, he gives a very beautiful algorithm to solve this problem in order n to the d over 2 when d is bigger than 3, when the dimension is bigger than 3. So by using our meta theorem and our quantum divide and conquer algorithm, we essentially follow the idea by Chen in 2013. But we have to notice that here the subinstance actually is we have to explicitly create it, which means it has no relation to the no much relation to the input. So we have to create a purely new subinstance. So we have to return it back to the quantum memory. Now we can reuse it for the following work. Yeah. Okay. And so by using our meta, so other parts can perfectly handled by our meta theorem. So by using our meta theorem, of course, we can solve it in we achieve almost a quadratic speed up when d is bigger than 8. Quadratic speed up is always our perfect, so perfect. And here's a second example, which is more famous. It's called the longest distinct substring, or AKA LDS problems. So given a string of n characters, we want to output the length of a longest substring whose characters are all distinct. So here is an example. It's 2, 3, 3, 4, 1, 4. As we can see, the 3, 4, 2 actually is a longest substring here. So that's why output is 3. And classically, people consider using dynamic programming to solve it. But as we know, or maybe just we don't know how to use how to quantize a dynamic programming-based algorithm. So that's why the first step, as a first result, we give a pretty new classical algorithm based on the divide and conquer. It achieves almost the same time complexity here, but it's better to using now it's better to use our meta theorem to solve it. But there's a main difference. There's a little difference here. Is that in all the sub-instance in our meta theorem create, actually is not explicitly, it's implicitly created, because we can use some index function, so mapping the any value of a sub-instance back to the original input. So we don't need to return it back to the quantum memory. So in other way, it means we don't need to use a QRAM here. So CQRAM is enough for this case. But for case coverage, we have to use a QQRAM. Okay. And another problem is why we can use our meta theorem to solve it, because sub-instance now is a union of, we promise the sub-instance is always a union of 2 substring of the original input. So compared to the quicksort, the sub-instance is also the union of some substring or subsequence. But for the quicksort, actually we can't know how to control it because it depends on the pivot value we choose. But here we can always promise is a union of 2 substring of the original input. Okay. So after so by our divide and conquer result, meta theorem combined with the element distinctness algorithm by Ambaylis in 2003. Actually, we can give this algorithm in a time order n to the 2 over 3 up to the polylog factors. And in a negative side, we can regarding the element distinctness as a special case of LDS problems. So that's why we can. So our algorithm actually is type up to the polylog factors. So here comes the summary. Okay. So roughly speaking, we achieve our favorite quadratic speedup for most of problems, but not for the LDS, because LDS has a bottleneck, which is element distinguished, because we use it as a subroutine. Okay, I didn't mention about the last two problems here, but they are also very interesting. And in case you want to know more about our result and yeah, you can refer to our paper on the archive. Okay, thank you.
Hello, thanks for the talk. I just had like a kind of broad question. So like, what would you say is like this essentially like the class of classical problems in which there's like a quantum speed up via divide and conquer algorithm? Like from the general procedure you gave, it seems like somewhere you could have like a Grover search or like some like quantum amplitude amplification or something. Like, is there some broader characterization of these problems that like would have a quantum speed up using divide and conquer?
Okay, so for example, in our meta theorem, actually, we'll only consider the case where the maximization and maybe some unstructured search, because when you do when you combine the results, you can always do something like a maximization or Grover search. So if you can see anything like take a maximum value or minimum value, definitely you can consider using the quantum minimum finding subroutine. But it's not always the case. For example, you have to control the errors. If a layer is very, so actually we use for the bottom-up approach, we use a two-layer quantum maximum finding. So we need to control the errors here. So if you have a bunch layers, so more than the two, or maybe some constant polylogarithm layers, then maybe you have low speed up.
Okay. Yeah. Thank you.
Thanks for the nice talk. I have a question about QRAM. So as you are concerning the time complexity, why you are assuming the time to access a QRAM to be O of log n square?
Yeah, that's a good question. I should mention actually the time here is depends on the implementation and the structure of the proposal, how to achieve, how to design this QRAM. But just like actually we don't consider how should I say? Yeah, but for this divide and conquer algorithm, actually we assume the square of log n actually is much bigger than the time to do. Does it make sense?
So you're considering like the O of log n depths of the like circuit implementation of QRAM?
No, we can go back to the slides. Sorry. Yeah, here. So, as we assume, actually the memory size is capital N here, and we can always boundary this capital N. So how the time to perform the memory exercise actually depends on the memory size, right?
Yeah.
The time depends on the size. So we can always assume this because for all of the problems here, the capital N is not so big. Okay, we use very less memories.
Okay, so I have another question. So whether this QRAM interaction is the dominant part in the time complexity?
Sorry again?
I was wondering whether the QRAM part is the dominant part in the time complexity.
No, because it's just polylog, and for nearly all the cases here, we consider it in a polynomial. This is just polylog.
Yeah. So okay. So in this case, actually, we don't have a QRAM of size like time complexity of log. We only have QRAM of depth in the order of log, right?
Log n. The depth log n.
Yeah. So actually,
what's its n?
What's
its n here? Sorry.
N is the size of the memory.
Oh, size of memory. Okay. Yeah, because I know we also assume this QRQW is some small number here, but not so small, and it depends on the memory size. Actually, I leave some details here. I mean, we have some very detailed argument in the paper if you want to have a look. Yeah, this is just for help the people to understand the high-level idea.
Okay, thank you.
Hi, thank you for your talk. I have some question about the minimization or maximization you specifically use. Do you refer to the Grover adaptive search as in 1996? Is that what you're talking about?
No.
Like,
should I mention about it?
No, you don't. Well, no. I'm just thinking about like, whether so when you, I'm sorry, I might not comprehend this correctly, but when you say you combine the results in divide and conquer, are you doing this quantum mechanically or classically?
Sorry, I don't get your question. So what do you mean quantum mechanically?
I'm saying, do you require to find the optimal for each case, like in a giant entangled state, or you just need to recalculate the oracle for each possible case?
Sorry, I don't understand your question.
Okay,
very well.
maybe we can talk about this later.
maybe we can take it
Sorry
offline.
about that.
Sorry for that.
Hi, thanks for the talk. Very quick question. So in your method, in your algorithm, you need the noisy quantum oracles, right? And there you have the condition that the noise you're just bounding by a constant, essentially. So essentially, when you're doing this divide and conquer step, do you also consider the case where the noise can grow as you're propagating?
Yeah. That's a very good question. Actually, I have already answered before. Actually, in our bottom-up approach, we only consider maybe 2 layers. You see, actually, so bottom-up approach, we just doing maximization over maximization and over the AT. So it's just a constant layers here. But for our meta theorem, actually, we consider more. You are right. Actually, when you're doing the maximization, the error will accumulate through the layers. But as we assume, actually, we only create h of n subinstance. So here's h of n. Actually, is a very sufficient large, since now we can reduce the errors. Okay, so that's very tricky here.
Okay, I think one last question.
Yeah, okay. Yeah, thanks for your very clear explanation. And I'm thinking that when I heard the divide and conquer algorithm, it sounds really like the dynamic programming. And I suppose that many of your algorithms, some of your algorithms based on my understanding, the optimal algorithm is use the dynamic programming. So what's the relation between them?
For this, since the dynamic programming and the divide and conquer are 2 different paradigms according to the tutorial, and then the idea is a little bit different. Both are to solve problems by dividing into some smaller problems. But for the divide and conquer, actually, it's recursively. Usually, it's a recursion. You use recursion here. But for the dynamic programming, you just started from a small case and to a bigger case, and you also have some sequential nature inside. So that's why we cannot quantize it. Usually, okay, does it make sense? They are very different, actually.
Can you explain more about that? Why you say that the dynamic programming cannot be quantized?
Because I don't know how to do it. Or maybe if someone knows, because let me know. Actually, we are thinking about how to quantize the dynamic programming. Maybe I should be careful. Actually, we can quantize the exponential time dynamic programming, but for the polynomial time, we don't know how to do it. Okay.
Okay, thank you so much.
Okay, let's thank the speaker again.